I want to use the example of merge sort to illustrate some interesting concepts in the analysis of algorithms, invariants, how to design, understand, and prove correct an algorithm. I want to illustrate some ideas of rewriting and reduction system, non-determinism, termination, confluence, normal forms. I want to show you how these ideas can be used to analyze algorithms at different levels of abstraction, and we'll also have an opportunity to discuss the efficiency of evaluation strategies and the time complexity of algorithms. Okay, so merge sort is all about merging lists. So let's look at this first. So you can see here that merge takes two arguments. And I give you an example here. So if you have two lists, 0, 2, 3, and 1, 2, 4, and we want to merge these lists, so how do we do this? We can think of having like a pointer here and a pointer here. And then what's the algorithm? So we compare the two numbers. So pick the smaller of the two numbers. Pick the smaller number. And so that's 0 here. Then we move the pointer. So let me move the pointer here. So I move it over there. And then we repeat. Repeat until end. So this is why we actually need an end of list symbol somewhere. It's not really in the notation, but lists have a special symbol for empty list. And the reason is that we need to kind of make a case distinction to know whether we reach the end of the list. Okay, so now we just continue this. So 2 or 1, we pick the smaller one, so we pick 1. And then we move the pointer. So 2 or 2, it doesn't matter which one we pick. So say we pick the left one. And so we pick the left one. Now we have to pick the one on the right because 2 is smaller than 3. So we have to pick this one. And then we move the pointer. And now what is smaller, 3 or 4? So 3 is smaller, so we pick the 3. And we move the pointer. So now the pointer is at the end. So it points to the whatever convention we use to label an empty list. So it could be the null pointer if we really work with pointers. And so here we take the 4 and then both pointers are at the end and we finish. So one question here is what is the invariant? Is there an interesting invariant about merge? And so while you're thinking about this question, let me just write it down. So question is, what is an interesting invariant of merge? I kind of give you a hint because I took sorted lists as my example. So there's nothing in merge itself that would require the two lists to be sorted. But the reason I took sorted lists is that if the input lists are sorted, if the input lists are sorted, if the input lists are sorted, the input lists are sorted, so is the output list. So that's an invariant. So why is this invariant important? Because it immediately gives you an idea of how you can use merging lists for sorting lists. Right? So you start with lists that are sorted, you keep merging, and you necessarily end up with a sorted list. So let's look at this in more detail. So question, how to sort using merge. So here's an example. We have a list that has 4 elements, 4, 3, 2, 1. Obviously, they wouldn't have to be in that order. And so in order to use the invariant, we need to start with a sorted list. So how do we do this? Right, so the invariant is saying that merge is producing a sorted list if we start with a sorted list. But how do we start with sorted list if our list is maximally unsorted? So here's the trick. The trick is that we turn the list into a list of lists, all of which are sorted. So that's the trick here. So now all the inner lists are sorted. And we simply keep on merging from now on, right? So the first step is special because it's the one which creates the sorted lists. And now, actually, we can pick like any 2 pairs here. We could even decide on not respecting the order of the lists if we wanted. But let's just pick 2 possibilities here. So what we can do here is we can merge the first 2 lists, for example. And we keep the other 2 intact. Oops. And then now again we have 2 possibilities. Actually here there are more than 2 possibilities. And we can, what can we do? We can, oh sorry, I was going too fast here. So if you spotted this mistake, well done. So now, I can merge this list with this list, right? So then I get the 2 first, and then I get the 3 and the 4, just because of the invariant we just discussed before. And then, okay, so let me move this up here a little bit. And then we can finally merge the 1 into the other list, and we get this. Okay, so we don't need these lines here anymore. Okay, so there's another possibility. We can also say, if you have 3, 4, instead of merging the 2 into the list 3, 4, we can also instead merge these 2 lists here, right? And then we get 1, 2 here. And now we can merge this list with this list, and actually we get the same list which we already have. Okay, so the idea here is again that we keep merging lists, keeping up the invariant. The inner list, the number of inner lists gets smaller, so that's termination. Okay, so let's talk about some of the features of this algorithm here. Okay, so this algorithm, first of all, is non-deterministic. So we can see that it's non-deterministic because it's branching here, right? So we have different ways of different paths of computation which end up in the same result. So how do we know that we end up in the same result? So one feature of this algorithm is that it's confluent. So confluent means that whenever I have a divergence here, whenever I can choose to compute in 2 different ways, whenever I can open up 2 different paths of computation, then there's a way of joining them together again, right? So you see here that in this example, these two different computation steps can be joined again. So that's confluence. So then another interesting feature of this algorithm is that it's terminating. So how do we know that it's terminating? So this is because there's a way to measure the size of the computation, how the size of the computation decreases. And this is the number of inner lists is decreasing. Number of inner lists is decreasing with each step. So this is a kind of measure function which we can use to establish termination. And obviously the number of inner lists cannot become negative. So if the number of lists is decreasing with each step of computation, the computation must be terminating. So from confluence and termination, we can get the existence of unique normal forms. And what's the normal form here? So the normal form is just the result of the computation. And so normal form means that the inner list contains all the elements we have and is sorted. That's the normal form. Okay, so next thing that is interesting to talk about is that this non-determinism here can be exploited to increase the efficiency of the algorithm. So let's talk about that. In particular, maybe I want to look at going around here on the left-hand side, and I want to look at going around here the right-hand side. And I want to argue that the evaluation strategy that is behind the computation path on the left results in an algorithm of time complexity O(n) squared, whereas the evaluation strategy, which is behind going the right hand, choosing the right hand path, is O of n log n. So obviously this needs some justification, but that's what we are going to talk about now. Okay, so before we go there, let's just quickly talk about different levels of abstraction. So the heading here is building abstract machines at the right level of abstraction. And let's look at what we have here. So should we start at the top or should we start at the bottom? Both make sense. So let's start at the top maybe here. So we choose a color we don't have yet. Lately I'm fond of this color here. So let's start at the top here. So the previous diagram, every step was a computation step, was a computation of merge. So we can think of this level of abstraction as an abstract machine which has a basic atomic operation merge, and that's the right level of abstraction to talk about the design of merge sort. So this is the level of abstraction we're thinking about when we are designing merge sort, right? The invariance of the merge, the invariant that if the input list is sorted and the output list is sorted, that's the invariant that gave us the idea that allowed us to find merge sort in the first place. So this is design. And this invariant also gives us the correctness proof, right? So we know that we will end up with a sorted list simply because that's what the invariant forces upon us. It was also the right level of abstraction to discuss termination, right? So it's a very simple termination argument because the number of inner lists is always decreasing. So the algorithm must terminate. Okay, so But it's not the right level of analyzing the complexity, because the merging two lists depends on how long the lists are. The time complexity of merging two lists depends on how long the lists are. So the level of abstraction where each computation step is a merge is too coarse to analyze the time complexity. On the other hand, if you go to really low-level kind of machines, like the machine language itself, or maybe this will run on a JVM, depending on the programming language you use, that's higher level than the machine language, but it's still a too low-level language for an interesting analysis of the time complexity. So the right level of abstraction for complexity analysis is, I would say, an abstract machine where each computation step is a comparison. So let's count comparisons. So maybe you remember that actually merge sort is of time complexity n log n. So the point I want to drive home here is that this statement only makes sense if you know what you're counting, what you're measuring. What are you measuring when you say sorting is of time complexity n log n? And you have to know, obviously, that n is supposed to be the length of the input we are sorting, so the number of elements of the list we are sorting. But then you also need to know that what n log n is counting is the number of comparisons. Okay, so I hope you also appreciate that this very general idea of reduction systems allows us then to relate all these different levels of abstraction to each other, right? So for example, I can say one step of merge takes so many comparisons. And then how do I compare elements, right? I need to maybe load something from a register and then do some kind of bit level operations and so on. And then I need to write my result somewhere. So this would happen then on lower levels of computation. And yeah, so rewrite system, reduction systems give us a uniform way of looking at all these models of computation in one general framework. Okay, so now finally, let's apply all this to merge sort again. So why is it that, I mean, how could I possibly claim that one of the paths in the graph on the previous page has time complexity big O of n square and the other has big O of n log n? So let's draw a little picture here. So let me choose a different color again. Actually, what I want to do here is I want to erase these numbers just for now and just look at the tree. So what is the tree supposed to show us? So suppose we have a list which consists of 8, 7, 6, 5, 4, 3, 2, 1 in the wrong order, right? And now we want to sort it with merge sort. And one way of doing it is to take 8 and 7, merge it, then we get 7 and 8, and we do one comparison. So now, let's say we already know that we have 7 and 8 in one list, and let's merge the next element into that list. So how many comparisons do we need? We need to compare 6 with 7 and 8, and then we can say it goes in the front. So this is 2 comparisons. And so we can keep on merging element by element into these lists, and each time we get one comparison more, because each time the longer list on the left is one element larger. So this is the number of comparisons is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So now, of course, we need to kind of want to turn this into a formula, right? So if our list has input length n, what's a formula for what's a formula for the number of comparisons. And the way to do this is to think about it as follows. So if we look at, it's in red here, so 1 plus 2 plus 3 plus 4. So how can we find a formula which is kind of just like adding these, counting the number of dots in this triangle? These are called triangular numbers, right? Because when we start counting them, we get this triangular shape here. And that's a well-known trick, which is to mirror this triangle and complete the triangle to a square. So we just put the mirror image here, 4, 3, 2, 1, right? So you see that we have kind of the same triangle in red and the same triangle in blue. And that gives a square, and now we just need to count the number of points in the square, in the rectangle rather, and divide it by a half. So if we do this, we see that we have n dots here, right, and n minus 1 dots here. So the sum, right, is n times n minus 1 divided by 2. And the purpose of using the big O is that we can just simplify this and say, this is just n squared. This is big O n squared. So if you know that merge sort has time complexity n log n, you may be surprised at this point. Why is this n squared, not n log n? But if you look at our picture again, at our graph, at our tree, then you see that actually what we implemented here is insertion sort, right? Because we insert 6 into 7, 8, and we insert 5 into 6, 7, 8, and we insert 4 into 5, 6, 7, 8, and we insert 3 into 4, 5, 6, 7, 8, and so on. So this is really insertion sort, even though we used merge to implement insertion sort. Okay, so why do we say that merge sort has time complexity n log n, and this now corresponds to a different evaluation strategy, right? So we choose a different path through our graph, right? So what we just looked at was the graph here, the computation path here on the left, right? And now next we're looking at the computation part that corresponds to going around here. So let's look at this. Let's choose a different color again. So the idea is the same, right? So, but you see that we are merging now in a different elements. We merge the elements differently. So we start the same way. We have one comparison here, which comes from merging 7 and 8. But then instead of merging 6 into 7 and 8, we merge 6 and 5, and we merge 3 and 4, and we merge 2 and 1. And now we build this kind of binary tree of merges. So how many merges do we need to merge 7, 8, right, and 5, 6? How many comparisons do we need? So we think of the 2 pointers, right? A pointer on the 7, a pointer on the 5, and then we have to move the pointers to the right, and so this gives us 3 comparisons, right? So we start with 7, 5, and then we move the smaller one to the right, and then we move it to the right again. So this was 7 comparisons, and then we do one more comparison, and then we are basically at the end. And so this is, of course, the same here, right? And then if we merge these 2 lists into the big list here, how many comparisons do we need? Like 1 less than the length of this list, so 7. And so why does this give us O of n log n? So that's the question. So how do we get O of n log n now? right? So the idea is that on each level, we have less than n comparisons. Right, because all levels have the same number of elements. So maybe I'm lucky and I get less than n comparisons, but I mean, we are doing big O here, right? So the order of magnitude here is 8 or n on each level. So this n here comes from having n on every level, right? And so where does the log n comes from? So this is, the n is comparisons on each level. And so where does the log n comes from? And this is just the number of levels. It's kind of the phenomenon you always have if you organize your data in this kind of binary tree form. You can also see this, like, just if you crunch the numbers here, what is the binary logarithm of 8? It's 3, and you see that we have 3 levels actually exactly here. Okay, so that's it. Maybe we can just go quickly to the beginning and see whether I said everything I promised to say. So quick rewind. We looked at merge. We found an interesting invariant for merge, and that gave us the idea how to design merge sort. It also gives us a really good understanding of how merge sort works, and we could use the invariant to prove the correctness of the algorithm. Then we studied this algorithm using ideas from rewriting. So our algorithm was non-deterministic. It was confluent. It had unique normal forms, and it was easy to see that it was terminating. Then we pushed this idea a little bit further. So instead of analyzing merge sort in terms of a rewriting system where each computation step is a merge, we could also look at finer grains of computation. So we argued, obviously, that we don't want to go down to the machine level or to a level that is as low level as a Java virtual machine, but counting the number of comparisons, that's an interesting level of abstraction, and that led us to evaluating different evaluation strategies in terms of the number of computation steps, the number of comparisons, and we could see that choosing different evaluation strategies would lead to an implementation of merge sort which has quadratic time complexity or which has n log n time complexity. Thanks for watching.